Okay, so today we're gonna continue talking about the cut matching game, and does it work? And so cut matching game is a way to construct an expander when when there is an adversary. So think of yourself as a cut player. Like you think of yourself as a cut player, and in each round you choose a cut, and then a matching player need to add a matching crossing the cut. Yeah. So if a cut player choose cut A and B on round I, then the matching player need to choose a matching that cross this cut, right? And the size should be of size A, which means that everything on the smaller side is matched. And so it turns out that we will see that there is an algorithm for the cut player that just take log n rounds, and then you will get an expander at the end, no matter what the matching player choose is matching. And to do that, to prove this, we say that it makes sense for the cut player to follow this heuristic, right? First, the cut should be quite balanced, so that you add a lot of edges in each round. Like the matching add a lot of edges in each round, and it should be a sparse cut too, or contain some sparse cut, so that it fixes some sparse cut. Okay, so that we will actually follow this heuristic, but now to really make everything formal, to do that we will use like some random walk to argue things formally, and the process of a random walk that we will look at is the following, right? That is, consider that you start from some node v0, and in each round you stay at the same place. So let's say this is v0, and if in round I there is a matching here. So what you will do is you just stay at the same place with probability half, or you just jump to the node that you are matched with probability half, right? So, but if v0 is not matched, then you just stay at the same place in this round, right? If in the next round there is like a new matching, let's say something like this, in next round, then again you stay at the same place, or you jump to the match node of yours. And yeah, we will look at this pi of uv to be the probability that the random walk starting at u end at v after I step. And we want to say that after a few number of rounds, then with like a not too small probability from u, you will get to v. Okay, so let's see why this goal makes sense. And roughly speaking, I'm gonna say that this is because it means that you can mesh, you can embed a clique into your graph. And if you can do that, then it means that your graph is an expander. So this is still rough, like not quite vague. It's still quite vague. So let's try to prove this formally. I need to be a bit more formal. And so let's talk about one matrix, pi. So pi is just nothing but it's just that the uv entry of pi is just this probability. You just put everything into one matrix. Okay, and so if you look at the column A here, the column A of PI is just basically encode like how much the mass that originate from every node n at A at time I. So this is what it encode, right? So now the first thing that you can observe is that in the beginning this matrix is just identity. So in the beginning every node stay at itself, right? With probability 1. So P0 is just identity. Like these are all 1. And now let's look at round I. And suppose that A is not matched in this round. Then it means that everything that was at A in previous round would just stay at A. So nothing will change. So it means that the column A stay the same. Okay. Now what if like A is matched to B? So in round I, let's say that a matching player add a matching. This is say it again. This is just the PIUV. And this is the probability that the random walk starting at U and at V at time I.
Exactly I step.
Yeah, exactly I step.
Yeah. What is the strategy of the cut player?
I'm not describing cut play the strategy yet. I'm gonna say that there exists some algorithm for cut player such that at the end, this is going to be true, and I'm trying to say that okay, at least why we look at this goal. Yeah. So right now, once we have established that this goal makes sense, then we're gonna describe the algorithm. More question? All right. So, okay. So now what if A and B is matched at round I, right? Let's look at this matrix. So what I claim is that the way we set A and B, so if this is P I and this is P, this is Pi minus 1, this is Pi, and let's look at the column A and B. Then my claim is that how would it look like? It would look really that these two columns will really just be the average of, like you just look at the two columns from previous round and do some averaging and then assign it to be these two. So why is that the case? So let's look at this this equality. Well, what is the probability that what is Pi of UA, right? So you ask what is the probability that like the random walk that start at UI end at A after round I. So first if A and B is matched, then you will have that first thing is the mass that end at A from route I minus 1 will move out of A. Like with probability half, it will move out of A, and with probability half, it stay at A. So this is like the probability that it stay at A is half here. But also, you have another mass from B that can jump to A. With probability half, the mass from B jump to A. So this is why for every U actually, PIUA is just the averaging of this thing, right? And the same reason is true for UI at B, right? So you actually have that for every U, PUIA is the same as PUIB. You really just average. And because this is true for every entry, for every row U here, like we have that the row U, the entry U here, is just the average of entry U here. Like you add things and assign it here. So this is why the whole column is just the averaging. Like this whole column is just the average of the two columns here, and the same for the column of B. All right. So so what do we have so far? We have that if you have a matrix P minus 1, and basically in route I, you will have some matching, right? Some matching. And so what will happen to this matrix in route I plus in route I is that the thing that is matched will be like you average them. The thing that is not matched just stay the same. The column which is like if this column is not matched, then it's just stay the same. So this is the picture you have in mind. Okay. And and next, you should see also that the sum, if you look at the one column of PI, if you look at one column A here, if you sum over all U, sum over all this, it's going to be 1. And this is really like by induction. So, sorry. So, but what does it mean? It means that here it says that the total probability mass stopping at A after I step, the total mass is 1 always. And why? Because, well, there are just two ways that, like in the beginning, each column have mass 1 total. You might stay the same, which that it doesn't change, or you are like a averaging of two columns that have mass 1 in total. So the total mass on each column is 1 all the time. Okay. And now let's look further. So now I want to ask, like, suppose that I look at a graph at route I, and if I add a matching, add a matching here, and let's look at so they are matching, so MI. So let's just look at one edge in the matching, and now we can ask, like, what is the total mass that goes through the edge? Okay. So what I mean is that for each, like, there is a mass starting like that start from U and ends at A from previous round, then there will be some mass from A that move to B. So that I count that, but I count this overall U, right? So that I summing up overall mass from every node U that go from A to B, and also back from B to A. So what is that in total? Well, from A to B, it's going to be this mass, right, which is here, and actually the mass that go from A to B is actually over 2. So you have half here, and you sum over all node. And also the same from B to A. It's going to be like the summing over all U, the mass that was from that end at B and is from U over 2. That is how much you go from B to A. Okay. So if you sum over all mass that really like go from A to B and from B to A, it's just this thing. But you also know that, okay, this total mass is 1/2, and this total mass is 1/2. So basically, the total mass that goes through an edge is exactly 1, right? And it means that actually, so this is true for an edge in the matching at round each edge in MI, but this is true for every I. So so note that for every I, the mass, like the way we do the random walk, right? The mass go through a matching from round I exactly at round I. So in round I plus 1, we're gonna use MI plus 1, right? So it means that actually every edge in the graph, actually, if you consider this random walk that we've described, every edge actually have exactly 1 mass in total that goes through it. Make sense so far? This is we just really analyzing one particular way to do random walk when we do a random walk starting from every node at the same time.
Matches have common edge, and in the final graph we have parallel edges.
In the final graph, we may have parallel edges, yeah. But in each round, it's gonna be disjoint edges. Yeah. Like it's a matching. Okay. So now, once we have really have some intuition what is going on with this random walk process, now we can prove formally now that if this is true, the goal that we say we want, if after the last round, the mass from U ends at V with probably at least something like 1/n, not too small, then it means that we can embed a clique into G. So K here is just a one product graph. So all one vector product graph, which is really just a clique where each edge have weight 1/n, right? Okay. So you can embed this thing into G. Okay. So now I'm gonna prove this formally. And why is that? So if you look at if you just try to keep track of how the probability mass that originate at U is spread through this random walk, well, it's gonna look something like this, right? If you start with mass 1 at U itself, and if in round I U is matched, then the mass look like this. If in round 2 you have this, then the mass kind of spread you might not, you might, maybe only this guy is matched and this guy is not matched. If so, then this is gonna be 1/2. The total mass from you is gonna be like this. And so you just keep adding edges and keep track of how the mass spread. But now observe that this really corresponds to a multi-commodity flow that starts from U and end at start from U to each node V. So like you can define the multi-commodity flow such that the value of the flow is really the same thing as the total mass that you have sent from U to V. So how to define the flow? Just keep track of how your random walk move through the graph, right? Does this make sense? Like after the last round, when you have all of this mass, like you keep track of how the mass have spread from you to everyone else. You just get the multi-commodity flow from you to everyone. And the value of this flow from U to V is just this. Make sense? Okay. So, and now if you just look at this multi-commodity flow starting from every node U, this is going to be multi-commodity flow between every pair UV. And you know that the value of the flow from every UV is at least this. Then it means that it really just means that you have, it's really by definition that you have embed this clique, this scale clique into G, right? But so far we didn't talk about congestion yet. I just said that there is some multi-commodity flow that embedded the clique into G. Now we need to ask how much is the congestion. Okay. But this is exactly what we have just talked about. Like for every edge in GI last, the total probability mass that goes through an edge is exactly 1. Right? So that really corresponds to the fact that the total value of multi-commodity flow over all pairs of flow here, it goes through this edge by exactly 1. So this means that the congestion is exactly 1. Yeah. So we have this. Okay. So we will use this, but let me tell you a bit more. That is, actually, so we have this inequality, but we also have another direction too. And the reason is quite simple. The reason is just that the graph G, the graph that we construct, is just a union of I last many matching. So the max degree is I last. But if the max degree is this much, then we know that clique is like the most well connected graph with for this degree profile, right? Like it's the most well connected graph with degree profile 1. So if you scale up by I last, you will get this. So we really have that G is similar to a clique, which means that it is an expander. Okay. So now, okay, we have established this goal. This is the goal that we want to prove. And if we have this goal, then G is like a low degree expander. Okay. And now that there will be actually two algorithms to achieve this goal, or like the randomized algorithm actually will achieve this goal. But there is another one, which is deterministic algorithm, that will achieve something morally this goal, similar to this. But actually, I will present this one first because you will see that it's actually a bit more intuitive. And so before I tell you about this deterministic algorithm, I need a bit more notation. It's just nothing much. So we say that cut S is beta balance if both sides of a cut is at least beta n. And the expansion of a cut, so is defined to be the number of edges crossing the cut, but this is over the number of vertices on minimum of number of vertices on both sides. Okay, so this is similar to conductance, but not quite. Okay. So note that this is just the same thing as the D expansion I have defined before in class when this vector D is all one vector. Okay. But I will use this thing which is pronounced as psi of S. And the expansion of a graph is just minimum, like take all the cut and take the minimum expansion, just usual definition. So note that actually expansion and conductance are similar if the graph have low degree. Because the thing, if the graph has low degree, then the volume of S is just, well, it is always at least S, and it is at most D max times S, right? And because of this, you have this inequality. So why this is true? Let's say I assume that there is no isolating vertices. So the graph is connected, say. So that's why this is true. Okay.
And also, we assume that it is unweighted.
Yeah. The graph G is unweighted in this lecture. Yeah. But it's going to be kind of easy to extend thing to weighted graph. But yeah. Like you can ask about weighted degree and so on.
But the volume of S won't be greater than or equal to mod S if it's weighted.
Oh, you're right. So, yeah, this is going to be true if the weighted degree is at least 1. Yeah, thanks. Right. Good point. Sorry. Yeah. Okay, so basically it's kind of similar. They are kind of similar in unweighted low degree graph. And we will work with psi usually, because it turns out that cut matching game is more convenient for psi. Psi is more convenient for cut matching game. But because at the end, like this is the graph, the graph that we work today is going to be low degree. So you can think roughly about it as conductance too. Okay, now the algorithm. So there is a deterministic algorithm which is exponential time that do the following. Basically it says that, okay, take log n rounds, and then at the end the expansion of a graph is a constant, and which means that the conductance is going to be at least 1 over log n, because the max degree of the graph is log n. And now it turns out that for this deterministic algorithm, it really follows the heuristic that we have talked about in the beginning. And the algorithm is just here. In route I, if there exists a balance cut, which is sparse, take that. That's the algorithm. And do this as long as the balance sparse cut exists, take that cut. And if it doesn't exist, then we will do some cleanup for the last round. And the cleanup step is the following. If this doesn't exist anymore, I will prove actually that there exists a cut. There exists a cut here, AI, where this is not quite balanced anymore because the balanced sparse cut doesn't exist. But so it's a unbalanced cut. AI is quite small. But the nice thing about this last cut is that it guarantees that on the B side, on the bigger side, the expansion is already big. Like the induced subgraph of the bigger side is already an expander. Okay, that's the last cut. We will prove this later that this cut exists, but so if you cannot find any balance cut, you can find the last cut like this. And after this round, we actually gonna prove that once you add this meshing, where this is already like an expander, if you add a meshing, then you're done. And this is kind of in the homework already. Yeah. Okay, so because there are two strategies here, all cut except the last one and the last cut, we will need two parts of the analysis. Okay. And recall our goal, right? Our goal is to say that some kind of random walk will be like after this log-n rounds, then the random walk kind of mix. Like, so how do we prove that? We will need some way to keep track of the progress, and to do that we need some potential function based on entropy. So the potential function is like this. So why this is t? This should be v. So just for each vertex A and route I, yeah, the entropy potential of A at route I is really like, it's just the entropy of the distribution of, like, it's the entropy of this distribution. So you kind of, so which is defined to be like this, like a sum over all node U, take this probability times the log of 1 over probability. But you can see that this thing really kind of is an entropy. If you have seen it before, it means that it kind of measures how much the mass from A are like spread through every other node. Right. In route I, everything stays at A, so entropy is 0, and entropy is not going to be more than log n. Okay. Actually, it's going to be exactly log n if this is uniform. Okay, and which is similar to our goal. Yeah. And now the total potential is just, we just define it to be like you summing overall potential from every node. So in the beginning it's 0, and it's never more than n log n. Now let's analyze things. A question about the potential. Okay. So the claim is here. If A and B, the cut that we choose in route I, is a balanced sparse cut, is a 1/4 balance and it's quite sparse, then the entropy in total is going to be increased by at least n. So if you know this, then what does it mean immediately? It means that
Takes on order of log n now.
yeah, you cannot find this kind of cut more than log n many rounds. Yeah. So once you have passed the log n rounds, then you're gonna get the last, like in the last step. Okay. So let's try to prove this. So for any set A and B, not just this cut A, I, B, I, for any set A, B, if I look at, I define P of A, B to be just summing over all probability, from all A in A and from B to B. Just the total mass that start from A and N as B. Okay. And now, how much is this mass can be? Well, we know that it's going to be at most, the number of edges in the graph at this point of time, right? So we ask how much. So let's say take this cut A, I, B, I. We ask how much mass have been, how much mass start from A can end at B. This mass needs to go from A to B through these cut edges that have been added into the graph so far before route I. Yeah. And we know that for each of these edge, for each of the edge here, the mass have go through it by exactly 1. So now we only count one direction. So that's we still get upper bound by 1 when you want to ask how much mass from A goes to B. Yeah. Because this is the mass that goes through this edge in both directions is 1.
So we can write it directly equal to
half. Yeah, right. Yeah, exactly. So this maybe it's better to write it like this, I think. So this is true for sure. Yeah. Okay. And now since the cut is sparse, then we know that this thing is at most AI over 100, right? So we have that the total mass from A to B is at most A over 100. And this means basically that most of the node in A, most of the node A in AI still have most of its mass in AI. This is by Markov, right? So we prove this formally. So what do I mean by the edge, the node that have most of its mass stay inside AI? So I said that the node A in AI here, we said that it is confined. It's kind of confined if the mass from it that go to other side is still at most 1/10. So most of the mass is still inside A, which is more than 9/10. So think of it as A, and the mass from A is like this area. It kind of still stay inside A. Yeah. And now, now we just prove formally that most of the nodes, like there are more than half of nodes in AI that are still confined. And this is simple. Well, this is by averaging. Okay. So intuitively, so I will just keep the proof, all right? So intuitively, when A is confined, then the entropy of A, of the mass that spread from A, should be like small. Right? And now what will happen if we add a meshing, right? Then maybe look at this. If you look here, and if I add a meshing, then the matching edge should help spreading the mass from A, which is confined inside A, to the other side. And basically, the entropy should increase significantly, at least for A. Yeah. So now to formalize this idea, we can say that we can try to identify which edge in the meshing is like the guy that helps like increasing potential a lot. And basically we will say that a matching edge that connects U in A to V in B is A spreading. It's like it spread the mass from that start at A quite significantly. So formally we will define it to be like this. If this is an edge, this is AI, BI. If the mass at A that ends at U is like kind of big compared to the mass at A that ends at V, like it's bigger than twice. This one is bigger than 2 times this thing, right? So if like the mass of A, so this is like a mass, like mass from A that ends at U and the thing that ends at V. If they are so different, right? What you know is that after you add a matching and do a random walk, what is gonna happen? You will average them, right? So it's kind of it should increase the entropy quite a lot. Yeah, this is what happened. After you add a matching and do a random walk step, this is going to be the average. So, so basically it means what? It means that a constant time this mass from A that ends at U. Basically, this amount of mass move from U to V. Okay. And now we're gonna need one claim, one mathematical claim. So, which is here. So basically think of this thing as P and think of this thing as Q. So if P is more than 2Q, then I'm gonna kind of compute the difference, how the entropy change, right? So the entropy, like what is the entropy, like, okay. What is the entropy of like how much this term contribute to the entropy of A is just in route I minus 1 is this much, right? So this thing U and contribute to by this much. And also U and V contribute to the entropy at V entropy of A at route I by this much. So here I really just kind of look at how much what is the change. And basically it says that the change in entropy is going to be at least constant times P.
P plus Q by 2, right? It doesn't matter for constant factor. No, it's 2 times P plus Q, right? Because 1 for P and 1 for Q. It's 2 itself.
Oh yeah, thanks. Yeah.
2 times P plus Q by 2.
2 times P. Oh yeah. Oh yeah, so it's 2 times P plus Q by 2, so yeah. Good. Right. So this one can prove it, but the point, the intuition that you should have is just that if the difference in mass is quite a lot, then once you average it, then the entropy should significantly change, like increase. And by significant, it means that this is by how much. Okay. So this really corresponds to how the entropy at A change by an edge, by the matching edge, that is A spreading. Okay. So this is basically what we have now, that the potential change at A is at least, if you're summing up over matching edge, that is A spreading, is going to be like this sum. Okay. So you have a cut, and there are matching. Some of them is good, some of them is A spreading. Look at this, then how much does it increase is this much. Okay, so the last thing we want to show is just that this whole thing is a constant. Okay, so suppose that it is a constant, then we know we have that the potential change at A, if A is confined, the potential will increase a lot, and there are like a lot of confined nodes because A is balanced. So the potential will increase by n in total. So let's see like formally why this term is big, is a constant. Okay. This is just to interpret again, this is total A mass, where at the end point, like total A mass at the end point of A spreading matching edge. Okay. And to compute this, we can just look at here, like let's look at the total mass at the end point of every matching edge. So I mean, just sum here without this thing. Okay. Well, this is going to be like if you sum over all matching edge, you know that every one in A is matched. So So you have this. Just instead of summing over our matching from U to V, you're just summing over our U. And then this sum is exactly just total. It's really just total mass that start at A and still end inside AI. But this is confined. This guy A is confined, so that's a lot of mass. Now, let's look at the same thing, but it's only like that when you sum. Okay, so this is like all matching edges, and sum of this is A spreading, and now this is A non-spreading. So now let's look at this one.
A belongs to AI.
A belongs to AI. Yeah. Okay. Well, if it is non-spreading, we know that like the mass that end at U here is going to be like smaller than 2 times the mass at V. So the mass at V is going to be kind of not too small compared to U. So you kind of, let's switch, instead of counting the mass here, let's count it at the B side now. So it's this one. So V here is in BI. And now this is, what is it? It is in total. It's going to be at most total mass from A to B, I. But yeah, again, this is confined. So this is going to be small. So now it means that the total mass that kind of start from the A spreading guy is big. It's a constant. Okay, so this means what? This means that, yeah, just to conclude, we have that after one round, potential increase by n. So there can be at most log n many rounds when we find this balanced sparse cut. Question? Yeah.
So just want to ask, so if there's a vertex whose most of the mass is here and some mass is there, so you're saying there can mass that can go from this side to this side as well, but because only some mass is in the other side, the thing which can go is twice of that small, like 2 times 1 over 10.
Sorry, I don't quite understand
So
this.
because already we have a lot of mass, so we already got 9 over 10. What is this 2 over 10?
Oh, 2 over 10 is the mass that, the mass from A that have already crossed to B. Like the mass from A that go to B is at most 110, right?
Yeah.
This is the definition of confined, and you have two. The factor 2 here is just because of this is non-spreading edge. For non-spreading edge, you have that this thing P is at most 2Q. Yeah. Right? Yeah. Did I answer?
So you're basically saying the amount of mass going back from BI to AI is less.
Back from AI to BI.
BI to AI.
I don't think I have analyzed how much it go back from BI to AI. Yeah.
That is the 2 by 10, right? So 9 over 10 can go from left to right and...
No. 9 over 10 is just the mass that start from A and still inside AI. And another 110 is from this node A that go to BI. Yeah. From previous round. Yeah. Yeah. Okay. Okay, so we know now that like we cannot find balanced sparse cut too many times. Now suppose that now the graph does not have balanced sparse cut anymore. Suppose that G does not have this balanced sparse cut. Now I'm gonna claim that something very good already happened. It means that it must mean that there is some cut A that like you can cut something small so that the rest of the graph is an expander already. And intuitively, this is kind of clear, but we just need to prove this formally. And how do I identify this last cut AB? The algorithm is going to be simple. Well, we can be greedy. Let's say that, okay, let's assign H to be G in the beginning, and A is just something empty. And so as long as there exists a cut which is sparse, and by sparse, I take it to be like 1 over 400 now. Okay. If you find this quite very sparse cut, then cut it and take this to be like A, like collect it into your set A, and then remove it from the graph. And find again, if there is another cut which is very sparse like this, cut it and include it into A. So keep doing this until you cannot do. That's your cut A, and B is just a complement. Okay. And now, just by construction, right? If this while loop stop, then the rest of the graph have conductance more than have expansion more than 1 over 400. We just need to say why. How come A cannot be too big? But the proof is gonna be kind of a bit annoying, but the intuition is super clear. The reason is this. So I'm not gonna actually show you the formal proof because you can look up, but the intuition is this. So first, if you have some sparse cut, if you have this guy where this is small, yeah, and if you delete it, and then you find another cut here where in the new graph, so this is G minus S, this thing is also sparse. So what do you know about the union of the two? Let's say both of these are like still small, like small side. Well, it's gonna be sparse too. And the reason is that, well, what is this thing? You compute the cut size here over the total number of nodes here, right? But what does this compute? This thing is this cut, and also this thing. So you can see that, well, this is the cut size, the blue cut size, the blue cut here. Yeah, blue cut H over S1 plus S2. But maybe I should say that this is, let me start, do this. And this is, so this is red, this is blue, and this is green. Yeah. So this is blue plus green, right? But this is at most blue plus red plus green. And this is S1 plus S2. But this ratio is less than 1. This ratio is less than this. So the whole thing, so this whole thing is at most this. Right? So basically, if you find two like sparse cut, remove it and find again, then the union of it is still sparse. Okay. Which means what? Which means that the cut A that you have collect so far, if each of them you collect it from a sparse cut, and you union this A together, it's going to be sparse cut too. Okay. And if it's too big, yeah, then that is the balanced sparse cut. So that contradicts the whole thing. So A cannot be too big. Yeah. And there is some subtle reason why I need to choose why I need to choose 1/400 instead of 100. This is because once you take the union of A again and again, then sometimes A become like, at the end, this whole thing become a bigger size of a cut. So we need to just do some annoying calculation and say that it's fine. Right, but you get the idea that if you start by saying that there is no balanced sparse cut, you cannot just keep finding some sparse cut and union all of them and say that it's big. That cannot happen. Make sense?
Even
Yes.
though A is at most n/4, so how can it be other side?
Oh, this is what I prove. Like the argument here is so that to claim that A is at most n/4.
Right, but A is the union of all the clusters.
Oh, so I mean, you mean because A is the union of the smaller side of a cut? How come A is big or what?
Yeah, I mean, even after unioning all these clusters, we have at most n/4. So, how can the issue you mentioned happen?
Because it is greater than node 4, that might have been already a sparse cut in the original, which we are saying there's no sparse in the original. Because of this argument, the union of all this set actually becomes a sparse cut in the original graph. So if the set A is greater than node 4, it is a sparse cut in the original graph as well.
Could you repeat your question? Maybe I'm not sure.
You just mentioned an issue regarding why we need the 1/400.
Oh, okay. Because I mean so how do I because if I don't have this, it can happen that once I union again and again, actually A is actually on the total size of A is on the total when you union everything, then A is actually, it can be bigger than this if I don't have this thing. If I don't use 1/400, then it actually can at least I don't know how to prove that A must be small. And the reason is that what will happen if
About the last thing.
yeah. like it can be the case that suppose that first round this is Si and the second round this is Si over 2 S2 sorry, so you have S1 and S2, so this in total, so both of this is the smaller side of the current graph, but when you look at the union of them, it's like a larger side of a whole graph. And there's nothing insightful here really. You just need to like flip the thing a bit and yeah. Okay. The point is just that when there is no balanced sparse cut, you can keep fighting. If you keep fighting sparse cut and union of them, it cannot be big. Yeah. And then the last step is just here by saying that if you have what we just said, that is, if you have that the graph is such that if this is AI and AI is small, and the rest of the graph BI is already an expander, then if you union this with a matching that connects all of AI to BI, then the graph will have high expansion too. The whole graph is going to be an expander. And that is in the homework actually, but I'm just gonna sketch it very quickly here too. It's just something like here. So this is just calculation again, but the intuition is just this. So let's say this is AI, this is BI. Okay. So there are two cases. So suppose that your cut is such that most of the thing is inside AI. So, and this part is small, like it intersect. Most of the thing is inside AI and not in BI. Here you know that by the matching edge, like some of the matching edge doesn't help this cut expanding, but because this part is much bigger than this part, you know that a lot of matching edge should go out of your cut. So that's why this cut is expanding. What is the other case? The other case is suppose that your cut is such that it intersect in the small part with AI and in the large part with BI. But here you don't need to even look into the matching edges. Yeah, the inside BI is going or like this BI, this edges inside BI is already expanding for you because BI itself is an expander. So balancing between these two cases, you're done. Okay. So why exponential time? This is just because like checking if there is a cut which is that have smaller expansion than some threshold. If you want to do this exactly, it's NP hard. So this algorithm that I just described, it doesn't work in polynomial time. But actually, it's quite easy to fix this because if you actually use an approximation algorithm for finding sparsest cut, then if you adjusting a bit, then it's gonna work. So you can try to check this like exercise how to use approx sparses cut.
Is that approx process deterministic or random?
There is a deterministic approx sparses cut. Yeah. And basically, yeah, in like 1 year or two ago, we basically show that like approx sparses cut can be done in linear time, and so actually this give you can make it work. You can make this deterministic algorithm become linear time algorithm. Yeah, that's possible. Yeah. But it's a bit complicated. So it turns out that there is another algorithm which is randomized and actually quite simple. And the running time is linear, near linear. And it says that after log n square rounds, the graph is gonna have constant expansion. Okay. So today I'm gonna describe what algorithm is. Maybe we don't have the time for analysis, but yeah, we will see the algorithm. So recall again, right, that how to look at this to describe this randomized algorithm. Let's recall how this matrix P evolved through times. It's just, yeah, as we have seen, the matrix P, Pi minus 1, if it is not matched, then it stays the same. If it's matched, A and B is matched, then the two columns get averaged. And by this relationship, we can actually define the matrix bold M, yeah, based on the matching M, such that Pi times Mi is Pi minus 1 times Mi is Pi. And this matrix is just like, this is how the matrix look like. So if the node A prime is not matched in this matrix, then you put 1 here. And if A and B are matched, then you put like this 1/2 to these 4 entries. Yeah. So Mi has like something like at most 4n non-zero or 2n, yeah, something, yeah, non-zero. And so you agree, right? This is how Mi look like. And so Pi is nothing but you start from P0, which is I, identity, and you just multiply it by M1, M2 up to Mi. And the column A of Pi is just this whole matrix times the vector, the indicator vector of A. Okay. Now we can describe the algorithm. It's something like this. So you will see that this is kind of similar to a power method. Yeah. But so in round I, you just sample a random unit vector. such that it is orthogonal to the all one vectors. So the sum of the entry of this is 0, of this vector R is 0. Okay. And now what you do next is that you multiply this random vector to this matrix. Okay. But this is nothing like how to interpret this thing, right? This whole thing is just pi minus 1. But we don't really compute pi minus 1 because pi minus 1, like the whole matrix might be dense, right? So, but this whole thing is pi minus 1. And you multiply it to Ri. Okay. And so this gives you some vector x where like each node u I, u1, u2, u3, and so on. It's like it's the embedding of node into a real line again, according to x. And what you do is you just find a median cut. Just sort the nodes according to x, and find them and return a median cut. So AI contains half of the node with smallest value according to x. Okay. Seems like doesn't make any sense. Like why this work at all? Okay, but let me at least today tell you why it makes sense. Yeah. So note that XA is nothing but like the projection of the column A in Pi minus 1 into direction Ri. Right? So the way to think about this is that maybe look at each node. And so each node has its own column, each node A has its own column vector in Pi minus 1. So this column vector, think of it as like some point in n-dimensional space. Right? A is at this coordinate. And then for each of the nodes, you project it down to the random direction. And the position of A as a projection is XA. Okay. By the way, this is not needed today, but because we return a median cut, so AI equals BI, the size are the same. So M is gonna be perfect matching, but we don't need it today. So why this thing has anything to do with the heuristic we talk about, which is to find balanced sparse cut. So recall this, like, do you remember the power method when we try to compute a sparse cut that have conductance like similar to square root of lambda? So in that time, right, what you start with is to start with the random vectors. Like it's not like now it's like random from a hypercube, but it's kind of morally the same thing, and it's like and you make it orthogonal to 1 too. And now what happened there? Recall that each node just update its value. Like you do a power method, but in that method, like when you multiply a matrix one time, essentially what happened there is that, like exactly what happened there is that each node, right, X is, you set it to be like this thing plus the average of your own your neighbor VU XU. That's what happened. So each node just update its own value according to some weighted average to its neighbor. And we discussed in the exercise session that once you do that several times, when there are like you start, each node start with a -1 or 1. And when you do this weighted average several times, that if there is a balanced sparse cut, suppose that there is a balanced sparse cut here, what happened is that the value of x, after you do average many times here, inside this is they're gonna have like similar value. Like maybe this whole thing have value of like more than 0, at less than 0, and this whole thing is more than 0. Like this is the behavior that will happen.